go. Okay. For starters, we're going to talk about something that we're going to start doing in the department to create a little internal competition. So my inspiration for this was recently I watched this movie on Hulu. And the movie is called The Art of Self-Defense. And it's hilarious. It's about this this guy who gets mugged or something, and now he's like afraid of everything, afraid of the dark, afraid to go out in public, and ends up stumbling upon this like karate school. And let's call it hilarity ensues in like this weird deadpan humor type way where, you know, he becomes a yellow belt and he gets like a casual normal yellow belt for his everyday casual wear pants so that he could feel like a yellow belt all the time. It's weird in like this most perfect way, and you have to watch it. If you have access to Hulu, at some point we're going to do we have to do a movie night and watch.
The most recent one, right?
Yeah, it's called with Jesse Eisenberg.
Oh, yeah.
Yeah, so you have to. Yeah, it's called The Art of Self-Defense. It is hilariously weird. If you've been by my office today, I have this thing up outside of my office. Let's see, can I zoom in? No, whatever. So the idea is this is the art of computer programming. And in 200, we're handing out white belts. When you graduate from 200, in 250, we're handing out yellow belts. When you graduate from there and you're in 300, you get orange belts. So I'm handing out orange belts to all of you today. When you graduate from here, you get a green belt, and then it's merit-based from that point forward. So as you continue to grow in your programming martial art, you can earn your way up to a black belt. Right now we have one person in the department who's a red belt. That's Jack Michelet's. Let's see. Blaine is a purple belt. We might have a couple other purple belts. But in any case, so all of you are going to get orange belts today, and you have to wear it at all times, even in your sleep. Mr. Gonzalez will check. Yeah, Mr. Gonzalez will check. Perfect person for this. So today the class, and you've watched the Art of Self-Defense, right? Yeah. Great movie, right? Like in this weird way. Very weird way. Yeah. So now you get to feel like an orange belt all the time. So in 300, everybody starts off as an orange belt. So if you want, come up and get well, not if you want. Whether you want to or not, come up and grab your orange belt.
He said that when you take 104 for English, it covers 103.
Okay, that might be true.
I think that's what
actually hilarious.
Dana said, but I couldn't remember. But I'm going to double check with her, obviously.
Are we going to get the previous belts as well, so we can hang them up?
I can do that. Yeah, so if you want the previous belts, I do have them in my office to kind of catch you up. We're going to start doing this moving forward. So the idea is once you graduate from this class and you're a green belt, now we're pitting you against your classmates because you might be a lesser belt than somebody who's in your class because they're just better than you. So, and that's the way it'll be. And maybe sometimes we'll just randomly line up, and you have to get in belt order. Right? So I have a feeling I might take this to all sorts of crazy levels. Any of you read German in here?
No.
What does this say? I will make you strong. So that's also a quote from the movie. He tells his dog that he's going to stop coddling him. As he's walking away, he says, I will make you strong. Great. Okay, so wear your belt at all times. We'll do belt checks. Gretchen in the cafeteria has been notified to also do belt checks. So, not kidding. so, what's this?
How does she know who's CS? Because I don't think anybody else is doing
I think she knows quite a bit about, she knows kind of who my students are, but also if you don't have your belt on, even if you're not CS, I'm assuming, going to hit you. I mean, I'm not sure exactly what her form of punishment might be, but
I'm assuming this is
Gretchen can be a bit rough and tumble. Okay. So that's the deal with the belts. The 200 students this semester are getting handed out white belts. So as you pass them in the hall or something like that, you can make fun of them. You know, get to class, white belt. You know, something like that.
For promoting bullying.
Well, don't actually hit them that hard. So.
Verbal will get them submitted.
We gotta take these quotes out of context.
Fine.
All right.
That's going on the soundboard.
That's going on the sound. That's also going on the sound.
Now, what's going to be great is if Elias shows up to class today, award him his belt. Let you guys connect the dots there. All right. So let's get back to we're using Ubuntu in here, right? All right.
Do we get stripes in our belts?
Well, actually, I'm working on that, so I'm trying to find a way to put a red stripe on my belt. Mr. Gonzalez actually has a black belt that looks red. You get a red stripe for every life you take. He's filled up his belt. Go ahead.
Is this a program, like basically life of a programming student, or like what exactly is
Well, this kind of merges two ideas. There's this, how many of you have read the Dark Tower series by Stephen King? There was a movie last year that was okay, but it didn't really capture. It's like an 8-book series, as Stephen King books go. It's got 4 zillion pages. And
16% of Rotten Tomatoes.
which
Not good.
which
Dark Tower.
oh yeah. That's why I said. I mean, it was, if you're a fan of the book series, it was an okay enough movie.
Yeah.
But you had to connect significant dots that because keep in mind this is, I don't know what the 8-book series has in terms of total number of pages. Let's call it, I don't know.
trying to adapt his book?
I'm sure it's 600 or 700 pages per book.
First one.
So I mean, a lot, thousands of pages, and they squeezed that into an hour-and-a-half movie. So you're gonna get what you're gonna get. But the hero in that movie, or one of the heroes, is this guy called the Gunslinger. And I've always kind of thought about programming as kind of like we're code slingers. And, gunslingers start off as kids almost like, Boy Scouts or something like that. And they learn the art of, you don't shoot with your eyes, you shoot with your heart and all this stuff. It's like a martial art type thing. And so all of you are now code slingers, and specifically your orange belt, code slingers. So I don't know, some kind of, mishmash thingy. Okay, so we've been working with, kill this here. Visual Studio Code doesn't like to come back from being put in sleep mode. All right, so there's our classes in here. We're going to continue to go through and talk about, for those of you who probably next year will end up taking the systems programming class, we write an operating system in there. So this is our loader for our operating system. You actually decide you're going to create your own operating system. That way you don't have to run those stupid Windows or Mac OS or Linux anymore. You just run your own. Very full featured. It's extremely full featured. Don't do it. All right, so let's see. So I'm going to bring up our DICE CPP here as we were going through it last time. So everybody was able to get their C program working for today. I know a couple people had some issues with copying and pasting. So keep in mind, if you copy and paste from one text editor to another, especially if that text editor is not a standard text editor, it will sometimes change certain things into other things. So for instance, a common thing you might run into is when something is surrounded by single quotes like this, and you copy this from one source to another source. This especially happens if you copy out of a PDF. It replaces whatever this single quote is with this like weird thing that I can't recreate on the keyboard, but it's another Unicode value that looks like a single quote, but it's not the single quote. It's got another name or something like that. It was like a circumflex or something like that. I think it has there's a name for it. It's got a little angle to it. But whatever, you'll sometimes get weird errors in your code related to that. So whenever you're getting weird errors that are saying, not recognized symbol like /408, things like that, it's kind of complaining about this Unicode value that it doesn't recognize. And chances are, if you copied and pasted stuff and it's complaining about Unicode values, you have some weird symbols in your code that you have to go through and backspace the weird single quote, replace it with the real single quote, that kind of thing. You could also just go and copy the weird one and do a search and replace, search for that, and then replace it with the right one, and then just do a replace all. That'll work as well. Okay. So a couple things here. When at the end of class last time, when I went to run this, we used none of those commands. Okay, that's fine. So I had you do, it was GCC, and then you did, I need to go into my dice roller CPP folder. So we ultimately created this output file called a.out. And what you had to do is you had to say GCC, and then we said dice CPP, and main CPP, and dice.hpp. What are we complaining about here? Oh, haha. Yeah, GCC is the C compiler, and we are compiling C++ code, so GCC is going to have some major problems with the syntax for that. So G++ is the GNU C++ compiler. GCC is the GNU C compiler, which is what we use in the 450 class. So that'll compile it. I don't think you need the HPP file. Go ahead.
Is GNU just like a type of compiler, so there's other compilers that you could use too, or?
GNU's the famous one. It's like this open source compiler collection. GCC is the GNU compiler collection. Okay. And so the default one is GCC, which is their C compiler. GNU stands for something. I think it's GNU is not. Let's look it up here real quick. Oh, Oh yeah, recursive acronym. GNU is not Unix. So it's, I don't know, it's this weird open source thing that's been around since the very early days of Linux, kind of one of our early open source projects. And GCC is their compiler collection. There are other products from GNU, but it's not a business, it's a open source community creation type thing. But it has become the standard, let's say. If you don't want to use GNU, I think CPP is on here. That's the proprietary but still around C++ compiler. CC is the version of that for C as opposed to GCC. All right, quick little reminder. I think I did this last time and you just saw me do it a few minutes ago, but I did it with the wrong command. If you have forgotten some command that you had typed and you want to find it, let me stretch this out so you can type in history, and history gives you this screen dump of all the commands you've typed in your terminal recently. So then you can say, I'm going to pipe that. So that's a vertical bar. So I want the output, instead of going to the screen, I want it to go to a command called grep, and then I'm going to search for G++, and that will show me my G++ commands. And then when I find one that I like, so for instance 237 here, I can say pound 237, and that'll repeat that command. Well, maybe we did need the HPV. Pound 236. The who what?
I think you referenced HTTP in the main.
But why are these guys having problems? G++, dice.
Did you mean pound? Did you mean exclamation point?
I meant exclamation point. Bang is the... Well, I don't think so. Because we didn't write that. We wrote the HPP, the CPP, we wrote the CPPs. What? I'm in the right directory, aren't I? Yeah, dice roller CPP. I really should be able to do it off of just main. Let's see what's going on here. Here's my main. Oh. So, yeah. Did I have some errors in it right now? This guy? Did I, I must have redirected one of my outputs to,
Oh.
let's see. Does the very bottom have our real stuff? There we go. What did you do? All right, so let's do that, then that, then that, then that.
Did Mr. Gonzalez actually type like 2,000?
It's like, what are you doing? He was dancing on the keyboard last night. This is Dice CPP. We actually want main.
No, it's clear that it's tap dancing. It must have had some sort of device. There's no way you could randomly type papers like that unless you knew
What is
the
going on? All right, here we're gonna cheat. We're gonna do this,
Leave everything.
and we're gonna do this, and we're gonna do this. What class is this? 300. Here is our main CPP. So I'm just going to grab that code there. We'll put it here. We'll save that. Then we'll come back in here. Okay, now it's complaining about the right stuff. All right, so here I said go ahead and G++ all my header and CPP files in that same directory. So it's kind of a cheat way of doing it. There's other cheat ways we can do. So enter number of sides, give it 4 sides, and it runs 10 4-sided dies. All right, so we're back where we were. So now let's walk through this and see how this guy is working, because we were rushing that at the end of class last time. And then we will go from there. Okay, so if you, I'm going to reference our driver.java here. So notice I've mentioned before all programs begin and end with main. So we have our main method here, and our main method takes in a string array here in Java. In C++, our main method takes in, this guy here is a array of strings, but in C++, arrays are not able to report to us how many things they have in them. So in Java, we can create an array, AR, and then say AR.length, and that'll tell us a number of elements in that array. So back here in Java, I can say elephant.length, and it'll tell me how many command line arguments were given to me in that string array. Make sense? In C++, that doesn't fly. So arrays in C++, being a much older language, C++ isn't able to report the number of elements in an array, at least not with a standard array. There's something called the standard template library that allows you to that has some upgrades to some of the normal C++ structures, but traditional C and C++ syntax, which is what we're using right here, doesn't. So this is, and remember from the end of class last time, if I go back here to our keynote, we talked about the special syntax we have for pointers. Pointers being variables for holding memory addresses. So I can define an integer just like I would do in Java, int a equals 5. But then if I want to get the address of a, I would put a little ampersand before it, and that will tell me where a actually lives in memory. And I can store that inside of a variable built for holding a memory address of an int. That is an int star, int followed by asterisk. That's an int pointer, a variable capable of holding the address of an integer. All right, so whenever you see the little star, we're talking about addresses. All right, so ampersand extracts an address, star holds an address when we're creating. Later on, if I want to print stuff, and this is pseudocode, this isn't how you print stuff in C++. We're going to look at that in a second. But if I want to print out the value of A, I get a 5. If I print out the value of B, I'll get a weird memory address because B is a variable capable of holding a memory address. That's what int star does. Int star holds memory addresses. Ints hold numbers, int stars hold memory addresses which point to numbers. So printing out B will give me a crazy memory address. But if I print out star B, that reads as give me the value that lives at the memory address stored in B. So star B resolves that memory address to its value that it points to. That make sense? So we're just seeing this generic syntax. So this is the syntax that Java had taken away from us, the syntax dealing with ampersands and asterisks. I'll call it stars over and over again, so just deal with it. All right, but Java took that syntax away from us because it no longer empowered the programmer to make the decision whether something should be passed by reference or passed by value. It says, look, we're going to do the heavy lifting for you. If you're passing something big, we'll pass it by reference. We'll give you the address where you can find it. If we're passing something relatively small, it'll be passed by value. So by default in Java, integers, if we're passing an integer to a function, for example, would be passed by its value. Whereas if we are passing, my example I always use is you're inviting me to your party, do you hand me the house or do you hand me the address where your house can be found? Okay, address is passed by reference. The house itself is passed by value. In C++, we could choose to give you a pointer to this house, which would make sense, right? Or we could choose to give you the house, which would never make sense in real life. But C and C++ empower us to do that as a programmer, which can be powerful. That can be a good thing sometimes for us to have that level of flexibility with memory. And that's why we still use these languages for working with operating systems, as well as some video games and stuff like that, when we're like, look, I'm not looking for automatic optimization. I kind of know what I'm doing. I want full control over what's actually happening because I know that the value I will find at this very secret memory location is the correct value, something like that. All right, so C++ gives us the power to deal with that directly. Java had taken that away from us. All right, so coming back here, printing out B, the value of B. B resolves to its value. Its value is a memory address because B is a variable capable of holding a memory address. Whereas if I say print out star B, that says give me the value at that memory address. If I print out the ampersand A, that says tell me where the value that lives in A resides in memory. Give me the address of it. Make sense? All right, so I have these two different syntaxes that allow me to either resolve a memory address to a value or resolve a value to a memory address. Yeah.
How come you have to specify what type is going to be held at a memory address? Because one memory address would be pretty universal, and like eventually when you use it,
The size of a memory address would be universal. So let me, to answer that, let's look at another example. Why does type matter? So let's say I'm creating a integer array versus a char array. So I'm going to say int AR of size 10. This is the syntax in C++. And similarly, I'm going to say char AR2 size 10. All right. Now we can actually create here, since we're working with our these pointers, we're trying to wrap our mind around it, and you've heard me mention several times that now orange belts are intimidated by memory, right? So most of us in here should feel a little bit uncomfortable with memory addresses, even though we're more comfortable with them now than you were when you were a white belt, right? I'm totally going to adopt this. And one of these days, I'm going to bring Mr. Gonzalez to class. And everybody's just going to start screaming. It's like,
Just flip everyone over on the desk.
What's really funny is you should see it at home, like this craziness. Like you think I'm just talking about Mr. Gonzalez is like this. Oh, him and I spent about 7 hours this past weekend watching Dracula movies. We're just sitting there. I actually had my wife go to the other room and get him. I didn't want to get up. But yeah, he likes the Dracula movies. The new Netflix Dracula trilogy is really good. Like shockingly good. Really violent too. He loved it. He loved it. All right. So in any case, orange belts are still going to be pretty intimidated by memory. So I'm going to show you a more intimidating way of writing what I just wrote here. So underneath here, I'm going to say, I want a integer pointer named AR. Okay, now a integer pointer holds a memory address for an integer, right? And I want this guy to equal. Is it still malloc in C++ or is it alloc? Let's just go with malloc for now, and then I'll update it later. It means the same thing. So I want to allocate some memory. This is kind of like our new keyword. All right, I'm going to allocate some memory. How much memory? I want 10 buckets times size of int. That's how much memory I want to allocate for this integer array. Now, if I were to print out, Sarah, I'll make this larger again so you can actually read that. So if I want to print out AR, I would get a memory address in either of these cases. The first one, the allocation kind of happens automatically for me. The second one, I am actually allocating the memory, which C++ empowers me to do. I'm saying I want to allocate some memory. And this is a function that takes some parameters. What it takes as a parameter is how many bytes of memory do you want to allocate? Well, I want to have 10 elements of type integer. Therefore, I want 10 times however many bytes an integer is. Integers are 32 bits in most languages, so that's going to be 4 bytes. So this guy will produce for me 40 bytes of memory. Make sense? That's what's happening under the hood, and the cool kids will actually define their arrays like this because they're cool.
So how did you get 40 of that?
10 times the size of an integer is 32 bits or 4
Right.
bytes.
Oh.
32 divided by 8 is 4.
Yep.
8 bits per byte. So 4 bytes is the size of an int. 4 times 10 is 40. This is going to allocate 40 bytes of memory somewhere in RAM. That's what malloc does. It talks to the operating system, says, hey, I need 40 bytes of memory. Tell me where I can find it. It'll give you the base memory address of that, and we're going to store that inside of this variable called AR. Make sense? Similarly, I can say, char pointer AR. Here, let's call this guy AR2 for clarity. Char pointer AR2 is equal to malloc, and I want 10 times size of char, like that. What's the size of a char? Primitive type. There's two answers I'll accept, and then I'll tell you which is the correct for C++. Because actually C++ and Java have different answers to this question. How big is a char in Java, which is what we know about? What kind of values do chars hold?
Characters.
Okay, sort of. They represent characters. What kind of values do chars actually hold? Okay, and Unicode values are what? Tell me about Unicode.
They're unsigned. Unsigned
You're getting there.
integers.
Unsigned ints.
It's like
Okay.
Like how many is like 20?
Because there's 65,536 unique Unicode characters, right? There's a big character map. So there's 65,536 unique characters. And we represent them by saying character 1 is this guy, character 2 is this guy, character 3 is this guy. So chars actually hold numbers which correspond to a value on the Unicode. So some value between 0 and 65,535. All right. So in Java, chars are 16-bit unsigned integers because we don't need to hold something below 0, only positive numbers. If it was 16-bit signed integers, it would hold values between negative 32,768 and positive 32,767. If you take the absolute value of both of those, add them together, you get 65,536. Everybody remember all those? All right, you don't have to memorize those. You can just figure it out by saying 2 to the 16th power or plus or minus 2 to the 15th power. It'll give you the right numbers. All right. And when you take the 325 class, you'll understand why there's one extra value on the negative side than there is on the positive side. It deals with something called 2's complement. Not this class, but whatever. All right. So, in Java, a size of char would be 16 bits or 2 bytes. In C++, it's 1 byte. Because it actually follows the ASCII character set by default. Consider the age of C++ predated Unicode by quite a bit. Why does Unicode exist, do you think? Why do we need 65,536 unique characters? English alphabet only has 26 letters in it.
Different languages.
Oh, other languages are important?
Different symbols. Different symbols.
The rest of the world is catching on now. It's just like, well, lazy Americans will just learn English. It's not the way it goes. But yeah, so we have the characters from not all the different languages. There's zillions of languages in the world, but many languages, as well as special characters. Kanji is in there, so we have some of the kanji symbols from Japan, and China shares kanji symbols, but they have some of their own too. So let's just say the symbols. But we have lots and lots and lots of different symbols and things. So we have 65,536 unique symbols that the Unicode character set supports. In olden days, the ASCII characters, American Standard Code for Information Interchange. So here, I'll put that here. ASCII. You don't have to memorize what it stands for, but this predates less than Unicode. Predates Unicode. It can actually, ASCII is defined as 128 characters officially, but it's stored in a byte, which can store 256 unique characters. So an unsigned byte is an 8-bit unsigned integer, which is 0 to 255. That's what can be stored in an unsigned char. All right, but punchline here is that this guy right here, char in C++, is 1 byte big. So this is actually requesting 10 times 1, which is 10 bytes of memory. Make sense? Go ahead.
Is there any sort of tool where like we could build a program for Japanese users without knowing their language? Using like Unicode?
Well, yeah, you can give them the, have them type in the Unicode number. Otherwise, you have to rely on them having a keyboard where they can enter the characters. So if they're using an English keyboard that doesn't have the symbols in it, they'd have to have a Unicode reference, or you can give them the 65,536 Unicode characters, or you probably can just figure out which chunk of those is the characters. Show them on the screen and say, pick your character. They'll put in the number, and it'll store as a char that Unicode value. But in our American operating systems, English-based operating systems, the terminal likely has a default setting of not being able to show those. So it'll show them as weird symbols. Trying to translate it, you'd have to get a universal Unicode terminal in order to do it. So another hand, go ahead.
Yeah, will it always be 10 times the size of whatever size?
I'm only saying 10 because I'm creating an array of size 10.
Oh, gotcha.
Yeah, if you want an array of size 1,000 or 15 or 17, you change it to how many do I want times how big is each one. Make sense? So these guys down here, these are synonyms for what's above, and they are working synonyms. C++ gives us the ability to work directly with memory. So I can say I'm going to create a character pointer. Character pointers hold memory addresses to a char, and I want this guy to be equal to whatever memory address is returned for me by malloc, which is kind of like our new keyword from Java. For when I say give me 10 times size of char. So find me 10 bytes of memory somewhere in the neighborhood, somewhere in RAM. Find me 10 bytes of memory somewhere, operating system. Operating system will come back and say, I found your 10 bytes of memory. This is where the front door is. This is the beginning of those 10 bytes of memory. That's what will be returned. We'll call that the base address. All right. So now we get back to his question of why does the type matter? So let's draw a picture here. Just cut that stuff out. And I'll go ahead and create this guy. There's my 10 buckets. And we'll make these guys, yeah, whatever. And then we'll create one more. And we'll make those guys red. All right, and then I'll copy this. We'll put this down here. And this is going to be our AR. And AR will point to there. And this is AR2. Which will point to here. All right. And just as a reminder, AR is 40, the beginning of 40 bytes of memory. AR2 is the beginning of 10 bytes of memory. So I'm just going to arbitrarily assign some memory location. We're going to say this guy starts at memory address 100, and this guy starts at memory address 200. We lucked out. That just happens to be the base address that malloc returned for AR and what malloc returned for AR2. So far, so good? All right, so with that in mind, we have AR is a thing built for holding integers, right? Okay, so this would be bucket 0, this is bucket 1, bucket 2, all the way up to bucket 9. All right. Now, AR2, if I say I want to go to bucket 2 of this guy, the syntax for that, and this works in C actually, so I could say AR at bucket, or AR2 rather, at bucket 2. That translates into go to AR plus. And I'm going to write this a little different than you have to write it in C++, just to really drive the point home. 2 times, here I'm going to put parentheses around it, 2 times size of, what kind of value lives in AR2? A char, right? 2 times the size of a char. So, and this is AR2, sorry. So the base address of AR2 is 200. So this is going to be 200 plus 2 times, how big is a char? 1 byte big. So this is going to say go to memory address 202. 201, 202, 209. All right, that's what AR2 at bucket 2 would look like. If I want AR at bucket 2, I'm going to go to the base address of AR, add to it 2 times the size of, what kind of value lives in AR? An int. So that's going to be 100 plus 2 times size of int, which is 4. So that is going to be 208. I'm sorry, 108. Base address is 100. So 100 plus 8, 108. So this is 104, 108, 112, 116, 120, 124, 128, 132, 136. So the reason the type matters is when I say to go to bucket 2 of AR, it knows to take integer size steps, 4-byte steps through memory. Whereas if I'm going to bucket 2 of AR2, it knows to take char size steps. 1 byte, 1 byte, 1 byte, so on and so forth. Does that make sense? So the syntax in the language allows us to say, go to bucket 2, 3, 4, whatever of the array, and it will do the underlying math. And we're seeing the math here by saying, oh, go to base address AR, whatever address that is, some memory address, and I want to go to 2 elements forward in that. So add 2 times the size of the kind of value that lives in there. Now the reality is C++ does not require this part. They don't make you do the multiplier. All you have to do is say +2. And that will hop you forward 2 spots off the base address, taking the appropriate size steps because we defined the right type. Make sense? So it will do the math for us. And we can choose to get to AR at bucket 2 by saying AR plus 2. We can do that. And that'll take us there. It's called pointer math. So this is the pointer math version of it. Now again, These are just numbers. Even though hexadecimal values, memory addresses look scary, they are just numbers, nothing more. Make sense? So if I have the number 100, which is a very not scary hexadecimal number, and I add 2 to that, I am at 102. But if I'm taking 2 integer-sized steps, I'm at 108. Make sense? I am walking from the first house to the second house, and integer-sized houses are like mansions compared to the tiny homes that chars are. Go ahead.
So if you're working with ints and say in like that top example you reference the memory address 102, will that still like reference the first bucket? Or
It'll reference the second half of the first bucket. So if this is a 32-bit number, this will give you the second 16 bits of that number, which for numbers smaller than 32,767 for sign values will be the same as getting the whole bucket, because that's where those bits live. But yeah, you're jumping into the middle of the house, so to speak. Okay, again, this is computer organization architecture stuff in terms of how memory actually works and how values are stored in memory. But yeah, the reality is if you go to memory address 102, that's a real address, right? Because usually memory is segmented into bytes. So I can go to byte number 102, and byte number 102 is going to have a 0 or a 1 there. That's what lives at byte 102. It's going to be the start of a little 8-bit little stint, right? And at that point, you're in the first 8 bits of the second half of the 32-bit value, right? Which C and C++ allow you to work with, but chances are you're not going to want to do that. More than likely, you've walked into a syntax error, right? Which then translates to what? It translates to this idea that, kind of the rationale of why Java was created, with the idea of taking the syntax of memory away from us as programmers. Because as programmers, more than likely, let's call it 99.9% of the time, we want to trust that our value starts here and ends here, and we don't need to know where it is. We just need to know how to get it, because we're building logical programs, a recipe for solving a problem. So we don't necessarily, almost all the time, need access to the memory. But it's kind of cool that we have it, right? So it kind of makes this hackerish type stuff. And to your point, when you're take the security class and you start talking about like penetration testing and various forms of hacking, getting into systems, a lot of times it's done by gaining access to the system, and then through a language like C, being able to get to special parts of memory that weren't meant necessarily to be directly reached. But you're doing it because you are purposely choosing to go to memory addresses that maybe you weren't supposed to get to. That make sense? There's some of you maybe heard of errors or vulnerabilities in software packages called a buffer overflow error. And a buffer overflow error says, hey, let's say that you have an array with 10 buckets in it, and you happen to go to memory address 17 of that array. So you're off the end of it. Now let's say that you happen to know that if you put something there, that's a place that some other system call references. You've injected a value into memory, replacing whatever value used to be there, and some other program that maybe has privileges significantly higher than you goes and reads this value that you've hidden away in a very secret place. And all of a sudden, bad things are happening on the system. Something like that, right? Okay, so does that answer your question about types?
Yeah.
And it's important because that's really what we're talking about right now is really wrapping our mind around this memory syntax and how memory works. And we're going to have to start filtering our thoughts through this idea of where we are in memory. But the good news is that C++ does the math for us most of the time and does give us convenient syntaxes like AR at, where's my AR at bucket 2? Didn't I write it in here? Oh, this guy. Does give us convenient syntaxes like AR at bucket 2 instead of forcing us to write the crazy but cool thing. Black belts write it like this. And then we finish it off with, is it a roundhouse kick? We got those? Is that a thing? Yeah, it's a thing. Only a black belt thing. I usually do mine leaping, but the ceiling's a little low in here. All right. So, jumping back over here, where we started this is arrays in, now, actually, based on what I just said here, this guy is an array, right? You've seen my syntax I wrote over here. When we define this, an array, we have this is fine. So we have an array, and this is how many elements are in the array, right? This guy doesn't take in a number of elements because that number of elements gets filled in by when this gets run. This takes in our command line arguments, okay? So somebody else is giving this guy value. Go ahead.
So is argc the same as argv?
No, we're going to talk about it here in a second.
Okay, sorry.
All right, so this guy is an array. What kind of value is this array built to hold? Go ahead. Okay, specifically what kind of memory address? Char memory address. This guy, and I typically don't like the syntax where they put a space between the char and the star, but you'll find it commonly written like that. I'll never write it like that. I like this saying, this is a char pointer. This is an array capable of holding this kind of stuff. In this case, it's a char pointer. And a char pointer is a pointer to a character somewhere. So if I have an array of char pointers, that translates into an array of strings. A pointer to the beginning of a string someplace else. Because a char pointer points to the beginning of a character array. Make sense? So this is a collection of char pointers. Each of those pointers points to the beginning of a string. So at each of those char pointer addresses, there's going to live another array. So if I draw a picture of that, go ahead.
So in Java, we always said that it was a string-based language, and strings are kind of superpowers. Is it the same as C++?
No, because we don't have as much. We don't have the tools to work with strings like we do in Java. So I would say that would not be a correct statement. So if I have this thing here, our let's just do, here's our main int arg c, and then char pointer arg v with the square brackets after that. Sometimes you'll see this written a little bit different way. You'll see it main int arg c char pointer arg v. So this is a char pointer to a char pointer. It's an array of char pointers that point to another char pointer. So we've removed, these two mean the same thing. They are synonyms for each other. You will see a lot of C programs written with this syntax down here. All right, I'm going to kind of give you a picture of how this is working. With the goal of we're kind of starting off with, when you look at this stuff, it's like, that's weird, that's intimidating, I'm going to go use a different language, to all of a sudden, this doesn't necessarily mean something difficult, we just have to draw a picture until we wrap our mind around it. All right.
That's supposed to be an array at the end, or
Which one?
after argv, are you supposed to?
This
have
one here?
The brackets or no?
This one here? No,
Okay.
because we have 2 stars here.
Okay.
But these mean the same thing.
Got it. Okay.
Yep. I only got 1 star here.
Okay.
Right. This is a 1-star char pointer, so I have the brackets. This one's a 2-star one, so the second star replaces the brackets.
Okay.
It means the same thing. I'm going to draw the picture here.
Got it.
All right, so we're going to have a variable here called argv. So again, both of these argv's here are equivalent. It's a different syntax meaning the same thing, and I'm going to point out why. All right, so this is argv. And this guy looks like an array. So here, we'll just assume 3 command line arguments because that will make me paste less. And what do you know? We also got memory address 100, but this is actually, since it's a char pointer, okay, so this is an array of char pointers. So now we have to ask the question, how big is a char pointer? Not how big is a char. We're asking the question is, how big is a memory address? Okay, so this kind of depends on the type of operating system we're dealing with. Are we dealing with a 32 or a 64-bit operating system? So if it's a 64-bit operating system, memory addresses, assuming your memory manager is also 64 bits, let's just assume that to be a truth, would be 64 bits or 8 bytes in size. If it's a 32-bit operating system, a memory address would be 32 bits or 4 bytes in size. All right, so in a 32-bit operating system, all your addresses get written on a little post-it note, all the same size. Whether it's a char pointer, an int pointer, doesn't matter. It's all the same size as the piece of paper you pass around with your memory address on it. If it's a 64-bit, use the jumbo post-its. But all the same size, whether it's an int pointer, a char pointer, a memory address has a size in the operating system. And that size is the same regardless of what kind of value that address points to. It makes sense? All right, so if we assume that this is a 32-bit operating system, actually, you know what? Just to keep the values different so we don't have overlap with ints, why don't we assume we're dealing with a 64-bit operating system, which is common today, right? Okay, most of our operating systems are 64 bits today. So we'll assume this is a 64-bit operating system, which means that we're taking double word size steps. That's a 325 thing. We're taking 8-byte steps. So 100, 108, 116 will be the locations in this array of char pointers. And each of these guys holds a value. What kind of value would I find in this bucket? What kind of value is argv built to hold? A char pointer. What do char pointers look like? Memory address. So this will be a crazy memory address. So I'm going to go ahead and good thing we only have 3 of these. And I'm just going to happen to use all right, we're going to put this guy at 700, 800, 900. We're just really lucking out here with Malik giving us nice numbers to work with. All right, so now each of these is a char. So this is 700, this is 701, this is 702, this is 800, 801, 802, This is 900, 901, 902. Okay, so this guy holds 900. I'm sorry, this guy holds, well, we could have held 900. So this is 700, 800, 900. In fact, let's write it that way. I'll make this 900, and we'll make this guy 700. It doesn't guarantee that they're in order in the operating system. All right, so that means that this guy here is a memory address which points to the base address of this string in memory. This guy here is a memory address that points to the base address of this string in memory. This guy is a memory address which points to the base address of this string in memory. Do you see now how this guy is an array of strings? So this is a collection of char pointers. Each of those char pointers point to a char somewhere in memory. And this char C has right after it the next character in bucket 1 of that string, bucket 2 of that string. I just purposely chose a bunch of 3-character strings here because I already had that as copy and paste. But if you really, really, really wanted this to be different, we can have a 903 here. And that could be cows. All right, so there's our four one, just to add a little variability in there. All right. So you see how argv is a string array? It's an array where every element of it is a string. Okay, so it's a collection of char pointers. Each of these char pointers points to another place in memory, which is the base address of a string. That makes sense? So when we say char pointer pointer, this guy says point to a pointer which points to a string. This guy says hold a collection of char pointers. They both ultimately mean the same thing. That makes sense? Okay, easy, right? Intimidating. But when you see the picture, it makes sense. So this is what we'll be wrapping our mind around as we work with this new syntax here. It's not difficult. We just have to not psych ourselves out when we see something. We're going to be dealing with a lot of memory this semester as we work with linked lists, stacks and queues, and things like this. All right, so now the question was asked, what is argc? I mentioned a little bit ago that in C and C++, arrays do not know how many characters they have in them, or how many elements they have in them. If it's a character array, how many characters are in it? If it's an int array, how many integers does it hold? So since arrays do not know, they cannot report themselves how many elements are in it, we need a second parameter that tells us the argument count. argc, argument count. This is the argument values. This is the argument counts. Argc is equal to argument count. Argv is equal to argument values. That make sense?
So the argument values are just the values, and the argument count is like what number the sign of that value?
By our examples here would be 3. Argument count is the number of arguments.
Yeah.
There are 3 of those. Bucket 0, bucket 1, bucket 2. And each of those points to an argument value,
Okay. Yeah.
an argument value, an argument value. So this is the collection of argument values, and there are 3 of those guys. argc tells us that.
Except for the bottom one.
No. This 3 here is the number of elements in here.
Oh, okay.
3 of them. There are 3 strings this guy holds.
Yeah.
This is string 1. This is string 2.
Oh,
This is string 3.
oh, that's.
It does not tell us how long these strings are.
Okay.
Now, it's very important that these guys are strings because there's something I'm leaving out here. I don't want to talk about it yet till we get into strings, but there's this 4th bucket here that has a \0 in it. \0 is the string termination character in C and C++. We'll get to that later. So technically, we can find out how long a string is by going to the beginning of the string, walking through memory until we hit a \0. End of string. It marks itself as the end of string. All right, but don't worry about that for right now because we're not talking about strings yet. All right, so we're good with this? All right, so let's try to finish up going through this guy here. So that's what this main thing is here. Now we're defining a string called S to write something out. So our version of print in C++ uses a library called IOStream, input output stream. So this is our output stream, kind of like system.out. So this is cout. So cout, and we use 2 less than signs, and then followed by our string, enter the number of sides. All right, so this will ask us for our number of sides without without kicking it down the line. If we want to have the equivalent of println, we would say that, \n there. You could also, you can also do that. Go ahead.
So that's equivalent to the print function?
System.out.println. What I have right now is system.out.println. This is system.out.print. Don't kick it down the line. Okay. Then we have a function inside of, I think it's in IOStream, is this getLine function. So getLine is like our scanner read line. Read something in from the command line. GetLine will use system.in. Remember in Java we say scanner input is equal to new scanner system.in. And then we say input dot read line, or it might be next line, something like that. So this guy right here is equivalent to these 2 lines here. So we're going to use standard input, cin, to read something into S, which is a string.
Those 2 lines basically are combined into that get line.
Yeah. Our goal here is to make the connection to Java. All right. Now I'm creating an instance of my dice class. S2I here is equal to integer.parseInt. This is string to integer. S2I. And you'll find that you have some other functions that are very similar to that do conversions between stuff. Now we have a pretty standard looking for loop. No surprises there. And this standard ... cout, this is actually not necessary because we brought in IOStream, but I'm leaving it in there because the syntax is something that we use. So this says use the library standard, call its cout function, and what are we going to output? We're going to output d.roll, and that's the same syntax we have in Java, right? Tell that instance of dice to roll itself, d.roll.
And keep doing it on each different line.
Yep, and then this kicks it down the line. So this is equivalent to system.out.println.
And it keeps repeating that.
D.roll like that.
Oh.
And then ultimately we're returning 0 here because main is expecting us to boil down to an int, because in Unix, a lot of programs have a return type. Did things work? Did it not? But we can just as easily make that void if we wanted to. All right, questions about this? All right, so for Thursday, I'm going to put up a little one-page paper assignment that's going to have you compare standard C++ to the new revision of C++, because we're going to probably bump into a couple of situations where we're going to have to use a more modern syntax of C++ that's tried to bring it kind of, sort of, maybe up to date with Java-ish, something like that. So this will give us a little introduction to it. Cool? Remember, today, student, faculty, staff, Bible study, God in grub, go to the cafeteria, sign in, get your tray, take it down to the terrace room. Free lunch, save your swipes, donate it to a CS faculty member. Well, let me stop the recording here.